Hello, good evening everyone. My name is Akhil. We are having this weekly live sessions for the course basics of minerals engineering every Tuesday from 7 to 8 p.m. For all full 12 weeks, we'll have this sessions. Okay. So this week we'll be looking at fatigue based problems, fatigue failure theories. So yeah, let's begin the session. Today's first question is very similar to our assignment problem. We have a circular stepped shaft on which there are forces at points B and C, and there is a steady torque, and it's at the stepped we have the concentration factors, fatigue concentration factors directly given. So now our job is to find what is the factor of safety for this system using modified Goodman's criterion. Okay, so please check the question once again. We are given the endurance strength, ultimate tensile strength, fatigue stress concentration factors at this point, and then the dias and forces acting on points B and C, and we were given A and D are simply supporting. So for this case, so first we need to actually see the stresses, right? So to see the stresses, we need to actually estimate the forces, reaction forces at A and D. Basically draw the bending moment diagram, and from the bending moment diagram we can estimate the bending stress, and because of the torque we will get the shear stress. So these two stresses will be there at every point, and because of that we'll see how the failure will be happening. Okay, so yeah, so I'm drawing as a single line only, and here one. So this is our step. So this dimensions is given as 50 mm, and one force here and one force here. So this is given as 100 mm, and this gap is also given as 100 mm, and this gap as 100 mm. Now these 2 points are simply supported, so there will only be a force, reaction force generated at this point. There won't be any torque because they are simply supported. Now this force is given as 5 kilonewtons, and this force as 10 kilonewtons, and the torque is given as 500 much 500 Newton meter. Okay. So now if we do the force balance, the reaction forces should be, the sum of the reaction force should be same as the applied forces. So RA plus RD should be same as 5 plus 10 kilonewtons, 15 kilonewtons. So this is one force balance. Now if we want to get the moment, basically we are given the concentration factors at smaller dia of the step. So at this point, so if you want to estimate the stress at that point, we need to know the bending moment at that point and the torque at that point, right? So if you want bending moment at this point, the easiest way is make a cut at this point. Now whatever moment is applied here, and then the force, by the other part of the system should be balancing this reaction force RA and the moment generated due to this reaction force RA. So this moment you can directly write as M is equal to RA into this distance, which is given as 50 m. Okay. So to get the bending moment, we just need to know RA. And how can we easily estimate RA? So if we do the moment balance from point D, then we can estimate directly RA. We don't need to worry about the reaction force RD. So let's try that. Moment balance at point D. So RA into 300 mm should be balanced by this 5 kilonewtons at 200 and 10 kilonewtons at 100, right? So 5 into 200 plus 10 into 100. So this is all in kilonewton and mm. So Newton meter never. Okay. So the reaction force RA would then be 1000 plus 1000 2000 by 300 20 by 3 Newton meter. No, sorry, kilonewtons. Okay. Now we know RA. So the moment acting at that point would be at the step. Let's say this point to be A, B, C, D. So E. Moment at point E would be RA into 50 mm. So 20 by 3 kilonewtons into 50 mm. So 1000 by 3 Newton meter. Okay. So now we got the moment also. Now what will be the bending stress if you know the moment in a shaft? Is 32 m by pi d cube. So is this clear? Point E I am putting at the smaller end of the shaft step. Yeah. E I am putting it the shaft smaller end. This I am denoting as E for our convenience. So that is the point at which we have to estimate the factor of safety. So sigma B is actually my by I. So that actually boils down to m into r is d by 2 by pi d power 4 by 64. So 32 m by pi d cube. So 32 into m 1000 by 3 into pi into the smaller shaft dia was given as 30 mm. So 0.03 whole cube. So this is how you can get bending moment. So you would actually get it as pi d cube. So almost 125.75 MPa. Okay. So this is the bending stress at the point E. Now what will be the shear stress due to the torque? 16T by pi d cube, right? So 16 into torque, it's already given as 500 Newton meter by pi into 0.03 whole cube. So this would be 94.31 MPa. Now one thing which we need to understand clearly is these forces are acting only from the top. Okay. So when the shaft is rotating, so if you consider rotating shaft, so from here this point force is acting. So as it moves, the point of the force with respect to a point on the shaft keeps on rotating. So this is actually comes out to be as an amplitude or alternating stress. Okay. So if you write the bending actual force, mean plus or minus amplitude. So this would be the bending stress acting at that point, and the shear stress would be, so just tau only. Now this tau is steady torque being applied. So this would be 94.31 plus or minus. There is no alternating in this. Okay. Now these are the actual forces being acting up there. Now we need to actually find the effective stresses first. Effective mean stress and effective amplitude stress. So if you are finding effective amplitude, so it from the principles we can estimate the effective stresses. Yeah. In this case it turned out to be that 94.31 almost. So this is how we can get the effective stress. Basically when I say effective stress, it's the von Mises stress. So our job is to first find the principal stresses for the mean and for amplitude separately. Okay. Now in the mean we have sigma bending as 0 and only tau is there. So in that case sigma 1 2 would be so because the sigma x and sigma y are 0, this would only be tau xy. So sigma 1 is equal to tau and sigma 2 is equal to minus tau. Okay. Now for this the effective stress would be tau square plus tau square minus tau into minus tau. So root 3 tau. Okay. So this is the okay. Let's do for mean effective is root 3 into tau. Now if you are looking at amplitude, sigma 1 comma 2 would be similarly here x and y are there, tau is 0. So 125.75 by 2 plus or minus root over 125.75 by 2 whole square. Okay. Now this would turn out to be so let me calculate these 5.75 by 2 plus square root. So this would actually be yeah, sorry. We already have directive sigma, there is not tau, right? So this is the actual stress directive. So sigma 1 comma 2 would be yeah. So 125.75 and 0. Okay. So is this clear? So this would give the sigma effective in the amplitude case to be 125.75. So this would be root 3 into tau. So root 3 into 94.31. So let me calculate that. Square root of 3 into 94.3. So 163.35. Now we got the effective mean stress and effective amplitude stress. Now using the modified Goodman criteria, factor of safety would be n is equal to 1 by sigma effective amplitude by endurance strength plus sigma effective mean by SUT. Okay. Here because there are stress concentration factors given, so we need to take that for bending and for shear. So because tau shear is only in the only contributing to the mean, so we can directly multiply only mean with the Ks, and the bending is contributing only to the amplitude. So you can directly put here, but in general you have to actually keep them during here itself. Okay. Because here only amplitude bending is contributing to amplitude, we are directly doing here. So this would be, what were the values? So 1.5 and 1. So 1.5 into amplitude is 125.75 by SG and 1.1 into Shear is 163.35 by SUT, 300 and something. So is this clear? You will get shear concentration factor, stress concentration factors. So you should actually multiply them here itself. Here itself. So this is bending. So this into kV, this into Ks. Okay. Yeah. So if you are doing for mean, this would be Ks root 3 tau into Ks, and this is bending. So this into kV. So that I did here, like while actually implementing. Okay. So because of the stress concentration factor, the actual stress would, you have to increase it by some factor. So that factor is Ks and kV. Yeah. Okay. So yeah, this is the final answer. Okay, here it's not. Yeah, let me. Oh, okay, okay. I'll upload it. Yeah. Now were you able to see? So what I did was based on, yeah. Now moving. Yeah. So based on the concentration factors, I multiplied the bending, whatever bending stress we got with kV, and whatever tau we got with Ks. Okay, Suresh. Yeah. Yeah. So I'm scrolling down, but it's internet. I think. Okay, let me connect to a different Wi-Fi. Okay. Is this what you are referring to? The final answer? Yeah. Okay. Now I think you should be able to solve your assignment problem also. It's very similar, but the numbers are different. Yeah. So we just first we calculated the reaction force RA, and then bending moment at E. Because of that bending moment, the bending stress. Okay. And then shear stress at that point. And now we multiplied the bending moment with the stress concentration factor and shear also with the corresponding stress concentration factors. And then we estimated the effective stress, von Mises effective stress for the means and for the amplitude separately. Okay. Yeah. And then we substituted those final mean effective stress and amplitude effective stress in the factor of safety formula. That's it. So it's just a lengthy procedure, but you can easily get step by step. Okay. So now, Yeah, it's not a constant. Okay. So now, next question. We were given the ultimate tensile strength, yield strength, and endurance strength, and the stresses. So whenever you are given this plus or minus, so first one is the mean, second one is the amplitude. So now we have to find the factor of safety using modified Goodman's criteria. Okay. Now factor of safety we know directly a formula. So A, when I write A, it's the amplitude and the mean. So mean by ultimate tensile strength and amplitude by endurance strength. Okay. So this is the modified Goodman's criteria. So amplitude is 50 by endurance is 120 plus mean is 80 by ultimate tensile strength is 500. Okay. So 1 by 50 by 120 plus 80 by 500. So 1.734. Okay. Is this clear, Suresh? Yeah. So now similarly the second one 1 by, so mean is 350 there, 350 by 500 and amplitude is 20 only. So if we substitute 1 by 20 by 120 plus 350 by 500. Okay. 1.1538. Okay. So if you see these two, actually in case 1 to case 2, amplitude stress is actually less. But because mean has increased so much, the factor of safety has reduced. Okay. Yeah. So next question. We have a steel bar and given endurance strength, yield strength, and ultimate tensile strength as previously. Now we have a steady torsional stress, alternating torsional stress, alternate bending stress, and factor of safety using modified Goodman's criteria. Yeah, so only if Soderbergh criteria we need to use the yield strength. Otherwise, we don't need to use in modified Goodman's criteria. Yeah. Okay. So now first we need to find the effective alternating stress and effective mean stress again. So if we write the torsional components, so steady is 150 plus or minus alternating is 100, and the bending stress there is no steady bending stress, it's just only alternate. Okay. Now mean effective stress. So sigma 1 comma 2 is equal to, so again in the mean only tau is there, so this would be tau 1 minus tau. So is that clear, Suresh? Yeah, because sigma x plus sigma, yes. So torsion has two components, steady and alternating. Bending only has alternating component. So first we are getting the mean effective stress. So to get the effective stress, first we need to find the principal stresses, right? So if you are looking at the mean, there is only tau. Sigma is bendings are 0. So this would means 0 plus or minus tau xy square. So 0 plus or minus tau, right? So in that case, effective stress would be root over sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. So tau square plus minus tau whole square, so tau square, so plus tau into minus tau full minus, so again tau square. Okay, so tau mean, which is 150. Okay, so in the mean case, because the bending stress is 0, that is why. Yeah. Yeah, so this I am taking as tau mean. Okay, now similarly we need to estimate the amplitude or alternating effective stress. So again, we get the principal stresses sigma 1 2. Here sigma y is 0, but sigma x is given as 120 and tau is 100. So 120 plus 0 by 260 plus or minus 120 minus 0 by 260 whole square plus tau xy square, tau is 100. Okay, so this would come out to be, let me calculate it, 60 plus square root of 60 square plus 100 square. So 176.62 minus 56.62. Okay, now again effective, no, so sigma x is this 120, right, and sigma y is 0. Yeah, so I am talking about amplitude means these two things. Tau is 100, sigma x is for amplitudes. Okay, yeah, that's okay, because we have written the formula before only. So now if we do that effective stress again, so square root of, let me do this calculation, 176.62 whole square plus 56.62 whole square plus 176.62 into 56.62. So 210.72 almost. Okay. Now again we got the mean effective and amplitude effective. So for factor of safety, modified Goodman's formula. So by endurance term and mean by ultimate tensile strength. That's it. So 210.72. So what were the tensile? 300 and 650. Okay. One by 210.72 divided by 300 plus 259.81 divided by 650. So 0.9074. So system will actually fail. Okay. Yeah. So now I think you should be able to, any system, you should be able to calculate the effective amplitude stress and effective mean stress and then get the factor of safety, right? So now we have a different question. So in all these cases, what we are saying is it is subjected to a single type of loading, either fixed mean stress and fixed amplitude stress. That's it, right? Now we have a system where initial 1000 cycles it is subject to for okay. Uh, say some component subject to first n number of cycles of one stress and then one more some number of cycles of the second stress. Okay. So we have let's say a shaft. So that is subjected to 200 MPa for 1000 cycles and then 500 MPa for 1000 cycles and then again 600 MPa for 500 cycles. In that cases, we have to calculate what is the factor of safety or will it fail or not. Okay. That kind of stresses, repeated different stresses. So in those cases, it's all clear now. The data given is at 400 MPa, it can handle 1000 cycles. Okay. So if you do more than 1000 cycles, it will fail with 400 MPa alternating stress. And at 200 MPa, it can handle 2000 cycles. Okay. Now the that same component you are subjecting only to 300 cycles of 400 MPa plus 1000 cycles of 200 MPa, and we are asking, they ask how many more cycles of 200 MPa it can handle. So let's take that as n cycles of 200 MPa. Okay. So what they are asking is what should be this n so that it will fail at how many cycles of extra 200 MPa will it fail. So in these cases there is one simple relation. So at 400 MPa we need 1000 cycles for full damage, right? But we are only putting 300 cycles. So effectively we can say that this damage is 300 by 1000. Okay. And next D2 1000 cycles at 200 MPa, it can handle 2000 cycles. So this is the damage due to the second repeated stress. And third also 200 MPa, it can handle 2000 cycles. So these are the three damages. And if it has to fail, the total damage should be 1. Okay. So if we substitute, so this will become 3 by 10 plus 1 by 2, so 0.3 plus 0.5. So n by 2000 is equal to 1 minus 0.8, so 0.2. So n is equal to so it can withstand extra 400 cycles. So is this clear, Suresh? Yeah. So these kind of questions, this is very easy to solve. But if you don't know that, you can directly take the damage and add them. It will be, we don't even know how to go about it. Okay. Yeah. No, there is no other way. This is the only, like this is the easiest way. We just take proportionality. Let's say it can handle 1000 cycles. If you are only doing 300 cycles, the damage for the 300 cycles is 300 by 1000. That's it. A simple relation. Yeah. Now next question. Yeah, this is a little complex question. Now we have component in the shape of large sheet. Okay, and then fracture toughness. We are given tensile yield strength of 500 MPa and Paris law coefficient and exponent R. Okay, and the number of loading cycles that can be endured if nominal stress varies from 100 MPa to 1/2 of the yield strength, and the edge crack had an initial crack length of 0.6 mm. So this is like we have a large sheet and we have initial crack. So in this case, now we are loading it with the alternating stress, fatigue stress. Now because of that, the crack length will keep on increasing, right? So now we are asked, they ask how many cycles, loading cycles will it need for the complete failure. Okay. So now that is the question. So first we need to, we are given initial crack length AI. Okay. So failure will happen when the fracture toughness value is reached. The if you look at the stress intensity factor K as beta sigma root pi a. So if this is equals to the fracture toughness, then that is the failure. Okay. So now we need to find what is this A which corresponds to this failure, like the final crack length at the failure first. Then we need to see how many number of cycles does it needs to go from initial crack length to failed crack length. Okay. So that is where this Paris law comes into picture. So first let's see to get this failure crack length AC. So because there is no geometry factor given, beta we will take as 1. Okay. And then we are given the stress is changing from 100 MPa to 1 half of field strength. So sigma is varying from 100 MPa to 1 half of field strength. 1 half of field strength is 500 MPa. So 250 MPa. Okay. So in the final crack length will happen when the stress is maximum, right? So at this stress, and geometry factor we are taking as 1. So and Kc we are given fracture toughness as 25. So that means 25 equal to beta is 1 into maximum stress we are taking. So let me write this. Fracture toughness would be beta sigma max into root pi AC, critical crack length or the final crack length. Okay. Now this is 25 is equal to beta is 1, sigma max is 250 into root pi AC. Okay. So now let's calculate this value. So 25 by 250, so this is 10. So root pi AC is 0.1. So AC is equal to 0.1 h2 by 4. Okay. So let me calculate this. 0.01 by 5. So 0.0032 meters. So 3.2. Okay. So the final crack length is 3.2 mm and initial crack length is 0.6 mm. So while the crack is growing, what are the total number of cycles that it can withstand? So that is what we need to find. Now this Paris law is basically relating the rate of change of crack with respect to the cycles as C into delta K power m. So this C and m is what they have given. And what is this delta K is the alternating stress basically. So sigma, this is rate of change of crack with the, that's what we'll see now. This delta K is this delta sigma beta root pi a. Okay. This Paris law is basically relates this changing stress, fatigue alternating stress, and the current crack length with the rate of change of crack length, basically rate of change in crack length with respect to cycles. Is this clear? Yeah. Now dA by dN equal to C. What was the value of C? 5 into 10 power minus 11 and m is 4. So C is 5 into 10 power minus 11 and M is 4. Delta K, beta is taken as 1, right? We are taking it as 1. And delta sigma. So we have stress varying from 100 to 250. So delta sigma is 150 MPa. Okay. So 150 into root pi e power 4. So is this clear? Now here we have only crack length A and with respect to the cycles. Only those are the independent terms which are available. Now we can do some manipulations. Yeah. C is given. This equation is Paris law. Yeah. C, the values are given. C and M values will be given to you always. 5 into 10 power minus 11. Yeah. So that I am substituting here 5 into 10 power minus 11 and M as 4 and delta K is beta into delta sigma is basically the range sigma max minus sigma min. So in this case 250 minus 100, so 150. Okay. So is this clear now? I am rewriting this power 4 to square root as a power square. Okay. So now 5 into 10 power minus 11 into 150 power 4 into pi square into a square. So now we can do this a square I am bringing to left side and n to the other side, right hand side. Okay. Into d. Now we have to integrate this because we know the initial crack length and final crack length. So the left side we would know and the right hand side would be initial cycle 0 to n number of cycles n. Okay. So if we integrate this from initial crack to this and then everything is constant, so 0 to n number of cycles it can we need. Okay. So a power minus 2, so 1 by minus 1 by a. So this entire calculation, let's see what it would be. 5 e minus 11 into 150 power 4 into pi square. So 0.2498 into n. Okay, so now minus 1 by AC plus 1 by AI is equal to 0.2498 into n. So basically 1 by AI minus 1 by AC is equal to 0.2498 into n. So what is AI? Oh, okay. So let me again disconnect and connect. Why it didn't share? Yeah. No, again wrong. Okay, let me try to log in again. My internet had some problem. So, yeah. Now are you able to see, Suresh? Yeah. So now I am just substituting the limits for the 1 by minus 1 by. Okay. So initial crack length is 0.6 mm and the final crack length is 3.2 mm. Right? So this would give n as 1000 by 0.24 into 1 by 0.6 minus 1 by 3. So 5421 almost. So these are the number of cycles you need to do till the failure. Okay. So is this clear now, this kind of questions? So in a large sheet we have initially already some crack, and now this is basically whatever we learned previously in the crack fracture toughness with fatigue. So that is where this Paris law comes into picture. So because of that fatigue loading, the crack keeps on increasing, and because of that increase, how many number of cycles we need to it can withstand. Okay. So first you need to find the final crack length. If you are already given the final crack length, then it's easy. Then you need to use this Paris law, and then substitute this. You will get this equation rate of change of crack with respect to the cycles in terms of the crack length itself. Then if you do further integration and some manipulations, you can easily estimate the number of cycles you need. Okay. Yeah. So yeah. Next we have one more question. So here delta sigma is given, dA by dN, Paris law is given. Again, we need to estimate the number of cycles for crack to grow from 2 mm to 8.8 mm, and here beta is given. Okay. So this is also similar question. dA by dN is equal to 0.66 into 10 power minus 8 into, we have delta k, which is beta delta sigma root pi a, right? So beta is 1.12, delta sigma is 140 root pi a power 2.25. Okay. So 10 power minus 8 into 1.12 into 140 into root pi whole power 2.25 and square root a power 2.25. This is dA by dN. And again we bring the a towards this side. So a power 1.125, right, is equal to d. So now if you do the same process which we did earlier, you will get the n number of cycles you need. Is that okay, Suresh? Yeah. So this is exactly same as last question, but here we are already given the final crack length, AI, initial crack length and final crack length. So we don't need to estimate the final crack length on our own. Okay. So if you solve this integral, then you would get the number of cycles. So we have one more question. This is the final question for today's session. So a component made of steel with ultimate tensile strength and corrected endurance strength is subjected to a bending load of in case A 250 plus or minus 100, in case B 250 plus or minus 200. Determine the life using high cycle fatigue and infinite life at 10 power 6 seconds. Okay. Okay, again this sharing has gone. Yeah. Okay. So previously when we have this SN cycle, in all those cases the mean stress was 0, right? In the last weeks whichever we did, week 6 and all. But now we have a mean stress. So in that case, how do we actually do? So that is the difference in this question. So when we have this mean stress and alternating stress, first you need to find the effective alternating stress in a way. So let's 10 power 3, 10 power 6. So this is Sm and this is Sv, right? Now for still what is Sm? 0.9 SUT, right? So this is the high cycle fatigue regime. So this point is 10 power 3 Sm and this point is 10 power 6 Sv. Now previously with these two data points, we were used to estimate the S is equal to A into n power B. We estimated these constants and then directly used them to estimate the life. But now we have mean stress. So because of that, we need to estimate the effective amplitude. Like to use this graph, we need to find an effective alternating stress. Okay. So that will come from modified Goodman criteria. So first let's just do this SN curve. So we have one point as 10 power 3, SM is 0.9 into SU2. Okay, let's just do this. So last time we did the same thing. Log 10A plus B log 10A. So if you substitute 0.1 and 2, this would be so this is 10 power 3 and if you substitute the endurance 10 power 6. So from this if you do the subtraction then it would become, so I'm directly writing this equation, so you can refer to our earlier weeks. So B is equal to now log 10 of Sm by Sc, so 0.9 into SUT 550 by Sc, that is 250 by log 10 of 10 power 3 by 10 power 6. Okay. So if you do this, you would get your BS minus 0.0989. Okay. Now to get A is any one point we can take Sg by n power B at 10 power 6. So 250 by 10 power 6 power minus 0.098. Okay. So that would give us 980.257. So now we have this equation 980.2571 n power b. So we in the last weeks we directly used this equation to calculate the life, right? If you know the stress, actual stress applied. Now we have, because we have mean plus amplitude, what we need to do is I will solve for case B. You can check for case A. So using modified Goodman criteria, the effective stress we need to put, first we need to estimate that. So that will come from, so whatever this stress, let me write it as this, okay. So we know the amplitude and we know the mean was 250 plus or minus 200. So this is the mean and this is the amplitude, okay, and SUT is given 550, right? So with this we will get the effective endurance stress it has to withstand in a way. So if you substitute that, so 200 by plus 250 by 550 equal to, so this would give you, okay, so 366.67 MPa. Now you can use this directly here to get the n. So number of cycles would be, so SCV by 980.2571 minus 0.0989, okay. So 366.67 by 980.257. So this will give you the cycles as so almost 20805 cycles. So almost 20,000 cycles. So this is how you can estimate life in the case when you are given both alternating stress and the mean stress. Is this clear, Suresh? Yeah. So if you do similarly for case A, so sigma m by SUT, sigma A by SAE equal to 1. So this would be SAE is equal to sigma A by 1 minus sigma m by SUT. So in case A, it is 250 plus or minus 100, right? So 100 by 1 minus 250 by 550. So this is exactly half of previous one. So 366 or let me just do 183.33. So one thing which you need to do see now is simple thing. This endurance strength is 250 MPa. So if anything below that, the life is infinite, right? Suresh? Yeah. So because we are getting 183.3, so n is actually infinite. Yeah. So I think this covers whatever this week's actual questions, which are not there in your assignment also, but might be asked in your exams in earlier assignments and other questions. Okay. That's it for this week. Yeah, because if I tell that, I am actually telling the answer, so I don't want to give this. So those theory based questions, you can think of it this way. So whenever this fatigue or whatever concentration factors, that question. So if you are talking about axial load and torsional loading, so see how the stress diagram would be. If you have a axial loading, entire part will have the same stress, right? Entire shaft. But when you have torsion or bending, only the outer dia will have the highest stress. So based on that, you can answer that question. Okay. Yeah. Last one. No? No. Okay.